Okay, let's look at the building systems overview. We will go into details of all these in many lectures. Today, I just want to give you the overall what we are talking about. Okay, so the first one is the basic design concept. I have shown you this slide many times, and I hope you remember this because I keep saying that the structural engineer's main job ultimately is this, to reduce the risk for disaster. So disaster, we talked about that, is made from these three components: hazard, which we will talk a lot, earthquake and wind and other things, and the vulnerability, which is the weakness in the structure or the strength of the structure opposite, and then the exposure, which is the planning part. And these two combined together have the risk. So our job is, like I said, risk reduction engineers. We need to reduce the risk. And to reduce the risk, we can manage somehow a little bit on the hazard side, and we can also manage on the vulnerability side. One thing that we will learn is that hazard can also be managed. Earthquake and wind forces are not constant like we normally think. These are external, but through structural systems, we can actually manage them. So we can not only increase the strength of the structure, but we can also reduce or manage the loading. We will learn that also. So anyway, so that's the main task. Our job is to do that, to reduce the risk of disaster and increase safety. We need to estimate hazard properly. That's the difficult part. And then we need to reduce the vulnerability to make the structure safe. The most difficult part is the first one, how to estimate the hazard. Loading, earthquake, wind, this is quite unknown, out beyond our control, beyond our knowledge. And that's why that's the unknown part. There are so many hazards that the structure should be designed for: earthquakes, volcanoes, landslides, glaciers, tsunamis, floods, wind, cyclones, hurricanes, tornadoes, forest fires, and building fires. So these are all things that as structural engineer, we must know how to design, because any structure is subjected to these hazards. Unfortunately, many times as structural engineers, we just think about dead load, live load, wind load, and earthquake load. We don't think about all of the other hazards, which are actually much more common. Floods are far more common than anything else. And landslides are more common than other things. And unfortunately, structural engineers are not trained to handle these hazards. And they're not taught, they're not understood well. And so they slip through the crack. Nobody's taking care of buildings against flood, against fire, against these kind of things. Okay. So as a whole picture, please remember that we have these all kind of earth, fire, water, air, and fire hazards all together to be considered. So when we design, we should, and the building codes are now becoming more aware of these kind of things. So currently, we mostly focus on these for tall buildings, but others are also important. In fact, other things are more important for low-rise buildings than tall buildings. But in any case, those hazards are still of concern. Okay, this is what we ultimately must ensure, that the building has these 10 things satisfied explicitly, one by one. Stiffness, we must have enough stiffness. Every concept should be clear on your mind. What does it mean? So you know what stiffness is. We talked about a lot. Stability, it must be stable, not run away, not fall down. So it's a global stability of the system and local stability of parts of the structure. This is a major concern during construction. Most of the things happen during construction, stability issues. And because the structure is not complete, so we don't think about the incomplete structure stability. We rely on the temporary works and temporary form work. That doesn't work, things fall down. So that's why we have to be careful about the stability during construction and post-construction. Strength, of course, we must have enough strength where strength is important. We must have controlled deformation where deformation is important. We talked about difference between strength and ductility and deformation in the last course. We have the beam that won't break kind of a concept. It can deform to a certain level, has a sufficient strength, and so on. So we learned a lot of these concepts there. Drift is one of the most important item in tall buildings. If you have to pick one out of these 10, you should pick drift as a control. If you control the drift, other things fall in place almost automatically. So one of the most important criteria in tall building design is going to be drift control, and we will measure many things related to drift. Drift means relative movement of two floors, how much they move relative to each other. And there are limits on that, and there are ways to control that. So drift, then comes ductility and damage together. So we have to have enough ductility, least damage. You remember sometimes damage and ductility are going together. Sometimes we allow damage to have ductility, right? So these will be very important for us, especially for earthquake. Damping is going to be very important because for dynamic response, damping is extremely critical. So we have to make sure that structures have enough damping. If not enough damping, we add damping or we remove damping. Damping changes over time. Then damping changes over the loading history and so on. So damping is not a constant number. So we have to watch for damping very carefully. Energy dissipation, another important thing we talked about, that when we are going to apply any hazard, energy is going to come into the structure, whatever it is. And that energy has to be either absorbed or dissipated. If you absorb the energy too much, when the structure fails, that energy will be released like an explosion. So you need to dissipate the energy as we go along. So energy dissipation is very critical. It's related to damping, it's related to damage, it's related to ductility. And then acceleration. Buildings will move, they have to move. These are very tall, slender structure. But the thing is how much they move, drift, and how fast they move, acceleration. Both of them have to be controlled. And one of the biggest concern in tall building now with the architects making them so slender is acceleration is not controlled. And people feel dizzy. And they don't feel dizzy because of during high wind or something. Normal wind can produce dizziness because of the crosswind effect. So we will study that also. But these are the 10 things. And when you make your project and you make your report, I want the report to include checklists that I have checked all these 10 things and I am satisfied with the design. And they all are within whatever limit we have. So these are the checklists, main performance criteria to ensure that the building that you're designing is going to perform well on these criteria. So now we have gravity, Apple thing from Newton. We have the wind and we have earthquake. These are the three primary primary effects on the tall building. And each one is going to fight against each other. The thing is that when you optimize something for one, it will de-optimize for the other. If you optimize for gravity, it might not work for wind. If you optimize for wind, it might not work for earthquake. If you optimize for earthquake, it might not work for wind. So these three concerns in a tall building are always going to pull the structure in different directions. And your job is to bring it together and one design that satisfied all of them. Especially earthquake and wind are completely opposite to each other, although they are lateral, but their effect is opposite, their design is opposite, their behavior is opposite, their concept is opposite. So traditionally, we can combine earthquake and wind in a load combination. It's not going to work because they are so different from each other. I mean, we still do that, but we have to understand before we go to that level. And same is the case with gravity. Gravity load needs different things. They want this, like gravity load is higher, they want a big beam, big slab, which is not going to work because it will increase the mass, it will not work for earthquake, and so on. So we will have to make sure that these three things are independently and jointly satisfying. So wind load is an actual load like this one, which is coming because of the wind particles are hitting the structure. And because of those particles hitting the structure, they create a force. And those forces will be direct and indirect. It will be crosswind, along wind, two directional forces will be very opposite. One is the force, like the wind is hitting the structure, so there's a force. And one is the wind is passing around the structure. And that will produce different forces perpendicular to the structure. Like the wing of the aircraft. When the aircraft flies, the reason it lifts up is because the wind passing over the wing on this side is pulling the plane up. Right? So it has no force is being generated along the wind because it's streamlined. But it's creating a lot of force perpendicular to that, which basically lifts the plane up. So we don't want the building to have that effect. So we don't want a streamlined building. Many people think we should make the building streamlined, but that's not a good idea, because if you make the building streamlined, you actually create like a aircraft wing situation, and the structure will start to move and float in the other direction. So that's why we have to make sure that the form is designed in a way that both a long wind and a crosswind response is controlled. So you don't want a streamlined building, actually. Earthquake, on the other hand, is a ground motion. It's not a force, and the structure generates the force by itself. So earthquake is not a force. This must be understood right from day one. Earthquake is a motion assigned to the structure at the ground, and then the structure decides to create the force or not to create a force. So we can design a structure in such a way that it creates no force, base isolation, or we can design a structure which creates a lot of force. So from very large force to zero force, we have the full option to do that. So for the earthquake, the amount of force generated on the structure is going to be our responsibility, is going to be somehow in our control. For the wind, same thing. Wind is coming, but how we position the structure, how we design the form of the structure, shape of the structure, and so on, so that we minimize both a long wind and crosswind response, balance them. So structures form, structures properties are now going to affect the load. They are not independent of the structure. So it's a load and structure interaction kind of a thing. And this doesn't happen for low-rise buildings. This mostly will happen for high-rise buildings. For earthquake, yes, we can still use it for the low-rise building also. And one of the reasons is that the design difference. For wind, we design in the linear range. We always keep the wind within the linear range. For earthquake, we design in the non-linear range. So the two are designed in opposite spectrum of the design response. And that's why they will never match. They will always be opposing, because one is designed within elastic, one is designed always in inelastic. So how can you combine two things which are designed on two different regions of the design spectrum, right? So this is the wind and that's the earthquake. So they don't overlap. And we will learn a lot about that one. Especially we will focus a lot. Professor Penning will also show you what this figure means. This figure is everything about earthquake. Yeah. So we will talk about that later. And the design principles have been changing. I've shown this slide before or not, I don't know. From intuitive design to code-based design to performance-based design to risk-based design and resilience-based design, and then beyond that, now we're talking about the AI-based design and so on. So you can see now that the seismic design is already going all the way up to resilience-based design. And wind design is catching up. We just reached performance-based design last few years back. Previously, wind was designed purely on code-based design. Now gradually, they are edging towards performance-based design. Earthquake has crossed performance-based design, consequence risk design, all the way up to resilience-based design. So earthquake is always ahead of the design, development of design methodologies, design principles, design equations. So earthquake design is far more sophisticated than wind design for normal buildings. For super tall buildings, it's the opposite. Earthquake has much little effect, but wind has all the effect. So at a certain height below that, earthquake governs. Beyond that, wind governs, and there is an overlap of certain region, depending on the location of the building, where both earthquake and wind will fight. And that is the most difficult region. And the 100 to 150 to 200 meter tall building are in that region, where earthquake and wind both are critical, and they're fighting. When you cross 300, wind will take over. Earthquake, you don't need to worry that much about. When you're below 100 meter, earthquake will take over. You don't need to worry about wind. But the 150 to 250 range, both of them, depending upon whether you're in Manila or in Thailand, one of them or both of them will fight with each other. Interesting thing is that some people do not recognize that low earthquake and low wind is not a good combination. People think it's a safe combination. It's not. And we will see later why not. Similarly, low wind and low earthquake, high wind also not a good combination. High wind and high earthquake is surprisingly is not a bad combination. It looks bad, but it's not. So we will talk about these differences when we go to that part. Okay, so that's the overview of the design principles. Now let's talk about the systems overview. Today is just overview. So structural system for a building typically has these components. We have core walls, we have shear walls, We have columns, foundations, combined foundation, wall foundation, we have slab, and we have floor beams. Typically, these components in a simple building. Of course, for tall buildings, we will introduce many more components to this one later. But basically, we need three systems for tall building to work. We need a gravity load resisting system, we need a lateral load resisting system, and then we need third system, which is not present in low-rise buildings, is the floor diaphragm. It is present in steel structures, steel buildings, not really present, or not really something that we need to worry about in concrete building in a low-rise structure. But for high-rise buildings, floor diaphragm will become very important. And that floor diaphragm basically connects all the vertical components together, transfer the load. So this is how the three systems can work. So the beam and slab jointly work to transfer the gravity load from where it is applied to the vertical parts of the gravity load resisting system, which is walls and columns. So they simply transfer the load from here to here, here to there, and then go to foundation. So that's the job of the gravity load resisting system. Normally we have slab and beam, but now beams are becoming out of fashion. So we mostly only have slabs. And then second is slab and beams, if present, they act as a floor diaphragm. This is a table, right? And these have two legs over there. And if I apply the load here, then this load from here must be transferred to those two legs through this slab in plane, right? Because I'm applying the load here, but it must be transferred to those two shear walls at the corner. So that means this slab must carry the load from here and to this one in slab. So this is the diaphragm effect. Because the mass of the slab is here, so the force will be generated in the center, and it must be transferred to the lateral load resisting system. And then the eccentricity will come in. We will study a lot about mass and stiffness eccentricity and all that kind of stuff. And that is from the floor diaphragm. So floor diaphragm and the design of this floor diaphragm has not been something new, maybe 15, 20 years old. Before that, people never realized that floor has to be designed for this in-plane forces. So now the diaphragm design for in-plane forces is another step that we need to perform, especially for tall buildings in a tower where it comes down and you have a large podium to, like, let's say there's a tower here, and then you have, at the ground level, you have shopping malls. And then from that tower, this shopping mall has a very different behavior. It will try to stop the tower, distribute the load, and so on and so forth. So we'll talk about that. So the floor diaphragm becomes very important in that case. And then, of course, you have the lateral load resisting system, which is consisting of the shear walls and the frames and many things. I put dotted line here because I showed you lateral loads can be transferred, resisted in many ways. Shear walls, diagrades, tubular system, so many things. So we will look at some of them. So we need to make sure that the gravity load is transferred using the least amount of weight or material. Because if you increase the slab, let's say by 10 millimeter, 1 centimeter, and you have 100 floors, you multiply that by 100. So you basically increase a huge amount of concrete weight over there. Anything that you do on one floor multiplies by number of floors. So each floor must be optimized for gravity loads. So each system has to be independently designed and checked. Now let's look at the tallness. What makes a building tall and what is the effect of the tallness? Why a tall building would need a different treatment? Why do we have a course today? And why do we have a full master's degree for tall buildings? Because of these issues do not exist in other buildings. First one is weight on vertical elements is a major issue. Like I mentioned to you, it's a challenge because everything just multiplies very quickly and adds up for the foundation until the foundation becomes impossible. Many tall buildings cannot be made because the foundation soil is not good enough. Why Manhattan has all the tall building? Because it's sitting on a rock. They don't have any problem. They can build whatever they want because right below there is a piece of huge rock. Ultimately, every tall building foundation must go to the bedrock. Some places it's very deep, some places very narrow. Bangkok is the other extreme. Mexico, Bangkok, where the bedrock is very, very far. So you need very deep piles and still you cannot reach the bedrock, right? So that's a challenge, right? But still people are making tall buildings here a lot. Thailand has, like top 10 in the world, new tall buildings. But it's still a challenge. Weight on the foundation, weight on the vertical elements will increase, multiply by number of floors. So it has to be managed either by lightweight or high strength material. So normally we use high strength material or lightweight material to solve this problem. Other one is an axial shortening of columns, because when you apply a vertical load, there is a strain. We talked about that in the previous course. And then normally that strain is 0.001 or whatever, very small. But if you multiply that by 100 meters, that strain suddenly becomes millimeters and centimeters. Now, what will happen is that if you, let's say there's a column here and there's a floor here, and these two columns, this column and this column have different weight. And for architectural reasons or for uniformity, the size is the same because we can't change every column size. So that means one column will have more strain than the other because stress is different. So which means that this column will now become shorter and one column will remain longer, which means the building will now have uneven shortening of the columns. Especially the core walls are very large normally. They don't shorten because axial stress is very low. Columns next to that are fully loaded because you want the minimum column size. So they become heavily strained. So the difference between a core wall and a next column, axial shortening could be as large as 20, 30 millimeter or more. That will change everything. The load distribution, more bending moments, and over time, many things will happen. Of course, in reality, this doesn't happen. Why? Because when they're making the floor, let's say they're on the 40th floor. So whatever shortening has happened already, they will level it off. So which means the columns are actually made longer than the core wall. And after they shorten, they become level. So this is something that we call the construction sequence analysis. So you have to do a special analysis to capture this effect, where the columns are actually made longer on site than their actual length. And after settlement, they become equal to the wall. So the slabs are made like this in theory, and then they come down. But in practice, we are just making those corrections on every floor, right? So this is very complex. And this changes the distribution of loads, distribution of bending moments, everything in the building. And that's why one of the important things that we need to do to handle that is the construction sequence analysis, nonlinear construction sequence analysis, which we will learn to do. Then exponential increase in wind load, because the wind load is reverse parabola. So when your height increases, first of all, the wind velocity increases by the square of the height. And then the bending moment increases again by the similar square. So then you have this very high increase of the bending moment as the building goes up. It's not linear, right? So because of that, after some point, the wind load management becomes, and it's not surprising that many buildings at the top are like this, like Eiffel Tower. Eiffel Tower was perfectly positioned to manage that wind profile. It was, I showed you last time, it was the shape of the Eiffel Tower was derived from the wind profile variation, even in 1890. So if you want a building, why Burj Khalifa is like this, and many buildings are like this. Okay. So they try to keep the wind force constant. Many times that will be not enough. So we will need to add smart devices to handle that, like dampers, different kinds of dampers. Then another problem challenge is multi-use. As I mentioned to you, that every portion is of a different type, which means different loading, different performance criteria, different grid, different arrangement is needed. Look at this building. This has a retail aquarium first. Look at that. There's an aquarium, like Emporium. They have a big aquarium at the basement, right? So we have a basement aquarium. Below that is a parking lot. So retail, aquarium, parking lot, restaurant, jazz bar, kids park, movie theater, concert hall, department store, duty-free shop, unrelated offices, conference hall. Look at that. In one building. Each one requires different space. So column layouts, columns cannot go through the movie theater and so on and so forth. So engineers have this challenge of always managing these change of layout, change of loading, change of criteria, and then the possibility that in future they must change to something else. They design something else, it doesn't work, tomorrow they change to something else. So that has to be incorporated into the design, the use change. So that's why another challenge is the changing grid lines, column offsets, column transfer loading, different load, different performance criteria becomes important for a multi-use tall building. Then slenderness, of course, is very obvious. The tall buildings start to become slenderness. So if H over D becomes more than 8, we consider building to be slender. New York, they recently made a building with H over D over to 22, 26. Extremely slender. You cannot imagine the slenderness of that. If you just one simple cantilever beam, the ratio is supposed to be L over 10. So anything over L over 10, even a simple cantilever is going to have a problem. Imagine a tall building with H over 22 slenderness ratio. So that means it's going to be extremely slender, very flexible for wind and earthquake and drift and deformation and acceleration. It's just going to be crazy. So that drift is going to be, we need to add special elements to handle that. We need damping devices. Period becomes too long or too short or too long. Crosswind becomes very problematic because building is always moving. The period, like natural period, is very long. The building will just keep on moving all the time, and people will feel sick, like the ship, sitting in a ship. So that's why it needs to flexibility. We need to increase the stiffness. Overturning is a problem. Building can just fall down, have to be anchored, and then with high acceleration, we have to add damping. So you can see that the slenderness is going to be one of the things that you need to manage. Then varying plans. This is another thing from the architects. Because of the aesthetics and because of the multi-use, the plan keeps, this is the same building, same real building, started with a floor plan like this, become like this, and become like this, right? So each floor is different floor. So everything is changing. You cannot design the same system and multiply by something. So this requires considerable planning in structure, eccentricities, construction sequence analysis. Some buildings are way complex, more complex than this one. Okay, I will show you. So we have a vertical load transfer, we have vertical irregularity, we have lateral force transfer, we have inclined vertical members. So everything that, if in a structure book, everything, do not do that, do not do that, do not do that, is present here. In the architecture handbook, do that, do that, do that. Instruction handbook, don't do that, don't do that, don't do that. So they just put together, and we have to then do things that we are not supposed to do. So ideal structural performance requires none of this, and architects want all of that. So that's going to be the challenge. Plan configurations, look at that. So building plans can be very different tall buildings. This is a very interesting building because the architect wanted a different form, and also the wind was a major problem. So they created two buildings. One, the real building inside, and one building outside, which is just only the cladding. So they changed the cladding to match with the architect's requirement and to basically to manage the wind and keep the inside building straight. And they created a gap, which is also very good for environment and all of that stuff, because you're buffered for heat and so on. So this is an interesting building that you have one simple plan inside and outside is changing. And you will notice one thing here, which I'll talk about, that this portion, this portion, this portion, the center, this portion, which is the core, right? And that's another main component of a building which does not exist for a low-rise building, which is the core. And we'll come back to that in a minute. So plan configuration changes, and with the core in the center. More plan variations changes. You can see from here, same building in different levels, how different they become. More plan configurations. Look at this building, look at that building, look at this building, look at that building. But you can see the core, big core here, triangular cores here, that kind of core, circular building. So you can expect very, very complicated layout plans. Okay, now the debate about structural system, one of the first one has been in the past, now it's becoming less important, is which floor system to use for gravity loads. Flat slab, flat plate, beam slab, whatever. But right now, we are not discussing that. I just want to tell you why this is so important. If you use RC beams, for example, and or you use RC ribs or steel beams or flat slab or no structure, that's what architects want. They don't want any structure. So if you are designing a building with this height, then look at that. If you use RC beams, then for a building for 51 floors, if the number of floors in the 200 meter will be around 51. So if the 200 meter is the limit, then they can make about 51 floors with a total height for 195. If you use RC ribs, you can add 3 more floors. If you use flat slab, steel beams, you can add 4 more floors. If you use flat slab, you add 7 more floors. Now, remember this, the selling price of the building is 10 times more than the structural price of the same building. So in Bangkok, for example, right now, the current price, roughly is about, let's say, 30,000 baht per square meter to make a building per square meter, right? The selling price is around 300,000 baht in good area, which means that if the client can make 8 more floors for the same building height limit, imagine how much money they can make, especially on the floors on the top, which are more expensive. So for them, it makes no sense to economize on structure, even though RC beams may be more economical, but they will go for a structure structure is less economical, but give them more area to sell so they can still afford it. Other thing is construction is the easiest thing to make for a contractor is flat slab, because you just make it, move it up. If you have beams, you have to make so many things, ribs, so many things. So no contractor will like that. And the current construction rate in Bangkok is typically 1 floor per week, sometimes faster. So they're making 1 floor every week. So if you have to make 1 floor every week, any small change, if changes that for 50 floors, you multiply by that, the project is delayed, you cannot sell it, you cannot get the income, and so on. So it's all about money, because they take the money from the bank, they have to pay interest on that. Any delay in project means money. Any reduced number of floors means money. Any lost space in structure means lost money. So ultimately, it's all about how much the client can sell, how quickly they can sell. So structural system selection is no longer based on only structural thinking. It has to be much bigger than that. And that's why many structural engineers do not understand. And they say, oh, this is very economical. It's not. For the client, it's not. That's why the total financial picture of the project should be understood. So that's why these days, now the bottom line is almost every tall building is now using flat slab, post-tension flat slab, not even simple flat slab, post-tension flat slab, so that it's even thinner than the other one. And if you go back to the building codes, you will find that it's not allowed. It's not allowed to make a flat slab in a post-tension flat slab in a seismic zone beyond 10 floors. Traditional codes are made that way because they are not for tall buildings. Those codes are for typical buildings. Okay, building form versus wind. Here you can see a completely opposite thinking of the two buildings, which are very, very tall. This is also very tall, and I presented that last time I just now also showed you the mega column building. And this is the other one. So here, this is optimized for wind completely. As you go up, building becomes smaller, smaller, smaller. It's the opposite of the wind profile. So there is almost no wind loading as go up. So the wind loading has been reduced grossly by the form of the building. But this one is opposite to the wind profile. As you go up, the building becomes bigger. And so the wind load is now increasing exponentially. And you can ask the question, why would they do that? Because 2 reasons. This represents a Chinese symbol, is a symbol called zun. So they wanted the building to represent that Chinese symbol, number 1. So it's about clients' thinking. Secondly, they can sell the top floors at a much higher price than the lower floors. So if there's more area to sell at the top, they can compensate for the additional cost that was required to make it. So finally, they decided against spending much more money for wind and then getting much more money rather than the other way around. So that's why these engineers came up with the mega frame system for this building. So decisions about forms, structural system are not based purely on cost or economy, because there are many other considerations for tall buildings. Now, form and response. So this is the two things. First of all, this building to that building, you will find many buildings doing that. This is a typical transition of the form from the base to the top. Many buildings do that. They start square as they go along, they become tapered, and they also, the corners are cut down. The corners are cut down basically to reduce the wind effects, crosswind effects. And then the height, the tapering is done once again to optimize for the wind loading. So this is a good optimized system for square to circular plans at the top. And this is a tapered form, again, from this one to that one. So this is used, this is architects use this as a design concept. Start with, think of the building ultimately to fit in this somewhere here. So that's why you see so many changing plans that fit this idea ultimately. So we reduce the mass at higher levels for lower seismic demand. We also reduce the area for the wind exposure. So it's very good both ways, because mass at top for earthquake is not good. We will learn later, probably you already learned. And then width at top is not good for wind. So both of them require that we reduce the size of the building at the top. But sometimes people go opposite, as I showed you earlier. So when we go taller, more slender towers rely on vertical structural elements to connect it to the core. So that's why the distance with the core becomes smaller and smaller and stiffer and stiffer. So the horizontal connection between the core and outer column becomes more stiff because the columns move inward, right? So, but there are, this is just concepts. I will show you later that almost all these basic rules are broken by people because of the other requirements that come in. So these are the ideal situations, you can say, to start with. If nothing else is important, we look at these ideas. And we will especially talk about this outrigger, which is like a tool we have to solve these problems. So this is the evolution of structural system. I showed you earlier from tubular to braced, same idea. This is actually from the book by Mark, what's his name? Sarkisian. And actually he might give us a lecture. I talked to him. He wrote 2 books. He's from SOM, head of their structural engineering now. And he has written several books on tall buildings. And I talked to him, and we might have a talk, online lecture from him on systems. So it is from his book, these pictures. So it's an evolution from simple tube to braced tube to diagrade, an evolution from tubular frame to mesh mega columns. So two directions. Start with simple tube or simple column and beam, add diagonals and become diagrade. Start with simple tube, change the shape, and then you come to the mega column concept. Just, remove things and move out. One is that you remove vertical. The other one is that you remove all horizontal members and just vertical members, put them together where the forces is needed. So these are all derived from, kind of an optimization of the stiffness. Where should it be placed? Okay. And there's a whole history behind them, but we will learn them as we go to these details later. So I created this small animation for you to see how we go from one to the other. Okay. So basic structural form, wall, we combine them, truss form, 3 forms. We combine this one together and we get the coupled wall system that we will talk about later. We combine the frame with more columns, we get the tubular systems. And then we take the tubular frame, we add the truss, we get the braced tube. And then we take the braced tube, we remove the tube, and we only get with the braces. So that's how we can create these systems from just the same concept that I showed you earlier. You just take the basic frame idea, and then you keep adding, subtracting, changing something, and you come up with these systems. So it's nothing completely new, but the concept completely changes. One is based on bending, other is based on axial load. One thing I told you before in the previous course, tension compression. If you can avoid bending by any means and convert the things post-transfer into tension compression, it will always be more economical than bending shear. So all of these systems are trying one basic thing: reduce bending, reduce shear, convert to tension compression. That's the end game. As long as you can do that, your system will be efficient. So these are the basic systems. You can see from the books many places. So we have braced frame, concrete rigid frame, 20 stories up to here, then 40 stories steel rigid frame, then concrete core wall, 40-story staggered truss, this story, and then you can see, and then you have the core plus outrigger going all the way to 140 stories. I don't think so, but anyway, they put it here, and core going all the way up. So these are made by people. Very rough idea of which system will work where, but it's not fixed. Sometimes we can use different systems even for other heights, depending upon how we optimize it. So this is it's a little bit old and approximate way of looking at structural system, because they say we can go up to 200 floors. So far, we haven't gone to 200 floors. But anyway, so this system, for example, core and outrigger actually doesn't go to 140 floors. It will be probably a little bit less. After that, the tubes will start. And these are the tubular systems, various tubular systems. This is more correct than the previous figure, because you can see here, this is a concrete frame tube, then steel frame tube, the tube in tube, and then concrete brace tube, then steel brace tube, steel die grid, and then exoskeleton that I mentioned to you, mega frame concept, then so on and so forth and so forth. So this is the final one, the super frame or the mega frame concept that we present. This can go very tall, because you can keep making them bigger, these super frames or mega frames, and then keep making them. So inside the structure is actually nothing. Each one is but you can think of this as one building with just 2 columns and these beams. Forget about inside. That's just filler. They're just hanging from these trusses. So this is a very different concept, that instead of considering every column to be load bearing, you just consider 4 columns to be load bearing, make them very big. Instead of every beam to carry the load, you just take those. So just convert the building from this one to that one, just changing the size of the beam, height of the beam. It's a very simple concept, but it works very well. And this this can go very far. So that's the idea. So these are some basic variations of the 2 systems. Next one is going to be our topic a lot we will discuss, is the outrigger concept. Real outrigger, virtual outrigger, and belt system. And if you want to get some more information, I just had it post on LinkedIn a few days ago. You can look into that, or also a webinar that we did. So this is one of the best tool you will have in your building range to optimize your structural system. How you decide outriggers, how you place outriggers, how you place the belts, whether you use real outriggers or you use virtual outriggers. So these are your, I would say, main tools that you will have at your disposal. I don't think you will get to design a building with tubular system very soon, because it's more than 300 meters. I don't think you will get to design a mega frame system very soon. Maybe you will. I hope you do. But it's unlikely immediately, unless you move to one of those firms to work there, which is possible, right? But the point is, most buildings will require this outriggers. So understanding outriggers is going to be one of the key focus of this course. So this is the one, again, a few examples of the building using the diagrids, just bracing. See, this is a mega column system with mega bracing. Very simple. This is the diagram building, the Gherkin, London. You can see here, this is first time they used on any major structure. This grid is architectural. The main grid is bigger inside. This is from the same company, SOM. These are the models of all the buildings that they designed. So in the office, they have a kind of a museum where they created the 3D printed models of all the tall buildings they have designed. And you can see how they developed so many structural systems, because Fazlur Rahman worked there, and then all his students or all his followers kept on working on that. So now they have the most interesting collection of, and the guy, Mark Sarkisian, he's from that company. So he will talk about this one, hopefully. So we can learn from the people who are at the top. Look at this building in the left-hand side. So this is perfect example of optimization called generative design. So they let the system find the best form. How many diagrades I need, not just put the diagrades everywhere, how many columns I need. So they start with a micro mesh that you see, that they put grids everywhere first, and they run the system one by one. Every element that doesn't carry any force, remove it, until they're left with the minimum elements, minimum vertical, minimum diagonals, minimum beams. So everything that is not participating is removed from the analysis and next cycle. So you keep generating the models every time by removing things which are not participating, and until ultimately you're left with the bare minimum, most optimized form. And this is an example of that. Lower, you have a lot of grades. As you go up, you don't need the grades because now the structure is laterally it's not a short building now. So you up on the top is a building with few diagonals, going down more diagonals, until you have this thing. It's beautifully designed. And this is another example where the building is actually going like this and core is holding it down. So to design the building like this is, you cannot design as cantilevers if you try to design, because no columns here. So this whole diagrid is a cantilever anchored to the frame, to the core. So when they make this building, in reality, after you finish the building, it will tilt like this because weight is out of balance, right? So they made it like this. During construction, it was not made straight. Because of the construction sequence analysis, they determined how much inclined they should make it, that when the building is finished, it will be straight, right? So these kind of things are common now. That building in Sri Lanka is a beautiful example where you have one tower, another one leaning on it, and this tower will push that tower the other way. So that tower was made like this. So when they connect, then it will become straight. This is designed by Moshe Safadi, the same guy who designed the Singapore, that building with 3 towers and the pool at the top. This is Zaha, the projects. Look at that. Just enough bracing determined from generative design, architecturally beautiful, following the natural form of leaves or trees or whatever you can call it, right? Because if you look at the leaf pattern is optimized, thicker, thinner, more branches in the end. A tree is the same thing. So if you take from nature, and she believed a lot, taking from nature structural forms and then putting them back into the building. So these are some of her designs for the buildings. Beautifully, just you can see this. You can see the structure and architecture at the same time. And they use the least amount of structure. They don't just decide what system they will use. They find what system is required. And these days, it's possible to do this, to do generative design for the buildings. But you have to work with the architect, and normally she and a few people, they just, be the architect and the engineer themselves or work closely. And this is, of course, the tubular system that I showed you for Sears Tower. So all these are based on, they start from 9 tubes and gradually reduce the tubes as you go up because you don't need them, right? So everything is optimized at the top level, not one beam, one column, one reinforcement. Many engineers think I'm going to reduce the reinforcement in my beam. Instead of 4 beams, 4 reinforcement, I will use 3 bars. That's no optimization. This is real optimization. When you optimize the form, when you think about the whole thing, and then you create something interesting. This is another one, outrigger, mega column, mega frame system. As I mentioned to you. So now people are working on these ideas and making really super tall buildings. So this is Wuhan Green Tower. Look at that. Few columns and few bracings. So one frame is just, you can think of it as a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10-story building. And inside 10-story building, every story has another 10 stories, so it becomes 100 stories. So they just put 10-story buildings on top of each other. Think of it like that. So that's the idea. So this is how you should completely think outside the box, not just try to think, oh, this is frame, this is shear wall. It doesn't work that way. I mean, it works that way, but if you want to really create something interesting, you have to stop thinking in that way. And this is, again, Dubai. The plan is a spine tube, the spine idea, once again, coming from a lot of studies. Just an interesting thing, when they designed this building, everything was completely designed, and they almost started the construction. And then they did the wind tunnel analysis, and they found that if they just rotate the building by 15 degrees, they can reduce the wind load a lot because the wind has a certain direction in Dubai. So if you orient, so everything was made ready to start, and then they did the wind load test, and they found that, oh, by changing 15 degrees, we can reduce the wind load. So they had to make everything again, the whole base plans and everything, because it was rotated 15 degrees a little bit, and that optimized the design. So it's not, like I was saying, it's not just the form, it's also interaction with the loading that you have to consider. Okay, so let's then finish this third part of the first topic. As I mentioned to you, that one of the key difference between the normal building and the tall building is going to be the core, which I highlighted here, which is the core. And core is where I mean, it's like the spine of the building, just like human spine. This is where the nervous system is. This is where all the strength is. This is, if the core fails, everything fails. And core is where everybody wants to have their things accumulated. And normally, there are some serious issues regarding the core design and core size. And the building that failed in Bangkok because of the core. And so that's how important the core for the tall building is. So the main difference between low rise and high rise I mentioned too is a service core. They call it service core, but we also call it structural core, or the core of the structural system. So it contains elevators and stairwells, heating, ventilation, and air conditioning ducts, plumbing, and fire piping, electrical communication, security, and everything. So everything in the building needs to either go up or go down from ground. And all of that has to come down to the core, and that's where the vertical transportation happens, vertical communication happens, vertical everything. The water goes up, and the waste comes down, the air conditioning moves up, air moves down, elevators go up and down, everything. And staircases are there, all of that stuff. So as you can imagine, that as the building becomes taller, more floors, more people, then more space is needed for the core. To some extent, then certain buildings have no space left to rent. That's why the core size is so critical. And everyone, all of these people are trying to find space within the core. And the architect's job is to reduce it as much as possible because they don't want to lose the rentable space, right? So this is one of the most difficult tasks of any architectural design, to make the core and the building usable. As you can see from here, that this is the core, and that is the building around that. Almost no space, the green space is so small compared to the core space, because everything is gone there. There are elevators there, there's everything, and then very little space is finally left, and that is a challenge. Now, for the structural engineers, we carry the vertical load through the core because it's the center of the portion, and we also carry the lateral load. And that is one of the reasons that you will see many structural systems are trying to move the structure outside from the core to the outer side. And I told you about the tubular system that was developed. The idea is that we don't rely on the core, at least move the structure out, so that the core, we don't rely, because core is shrinking and it's going to shrink, and I'll tell you why. The core is shrinking based on I think we talked about the elevator already, right? And now you can see here that the core is at different location. It is need to do many things. One of the key important part is evacuation, because fire engines, external fire cannot reach the tall building. So if there is a fire, then people have to actually evacuate in a safe place within the core, a place which is actually pressurized. That means there's a high pressure inside and there's a low pressure outside. So the fire cannot get into that. So it's always pressurized. It's closed and it's pressurized. So when you enter that space, that evacuation space, then you go through, even though there's fire outside, it cannot come into that evacuation space, and normally it goes down and then normally has to come down, and there are tunnels. If you look at the evacuation plan in a tall building, in a real tall building, highly complex and highly technical sort of design of that evacuation space. It's not just normal stairs. Okay? There are fire doors, and those doors, if you open them, the alarms will sound, and they're there are 2-3 levels of fire doors and many things. So you cannot see it, but there's a whole evacuation system working within a tall building, and that takes a lot of the core space, which you cannot even access normally, only available through emergency, because you cannot have external fire doors, or fire spaces, fire stairs. And that was one of the problem that was noticed in the World Trade Center. You might have seen the videos, people coming down through those are not safe from the fire, because that portion at that time wasn't developed properly. Okay, this is a building in Bangkok. It's called All Season Place, and then it's a 65-story building. And you can see from here now that the space actually used by occupant is quite small, and the core inside is quite big, having all those things that I mentioned to you. And so the structural part is here. Inside are thin walls. Normally, they cannot be used for structural purposes, because as soon as you put a wall there, it will start attracting shear. And we will learn later that the shear wall, bending moment and shear are distributed very, very differently. So if you remember in the first course, we talked about that if you have a web, it will take the shear, flanges will take the bending. So if you put a wall here, for example, here, and as soon as you put the wall here, it will start to take all the shear, because that's the main web inside. But the thickness is not large because they don't need the space. So which means that you have to build some of the core wall later and not make it part of the structure, only to contain something. So many portions of this wall that you see are non-structural. You cannot have a wall so thin placed in the core. So you can see there's an outer shell which is very thick. That is supposed to take most of the shear, and probably there is just this wall which will take the shear and outside the bending. So design of the core wall, which part is structural, which part is non-structural, which will take the shear, which will take the bending, is very critical. These are some other buildings with the core. So now some buildings, this is like this one. So the core, but core is off-centered. So, and it's not big enough. So you need more shear walls. So structural part of the wall is then distributed, not only at one location. So you because it's too small, then you add more of these black parts that you see. These are the structural shear walls, in addition to the core, when the core is not sufficient. Core is not sufficient typically in residential buildings, because residential buildings do not have all the services like a hotel has or an office building has. So that's why the cores generally for residential building are smaller than the cores in the commercial buildings or office building. Also, the residential building normally are larger in size, so it's distributed. Okay, so all of these will impact the design of the structure. So this is, once again, as you can see here the core is very clear. So these small portions in the inside, there are many walls, but the engineers cannot use those walls, because as soon as you use it, you have to make it thick, and then it takes up the space. So they are all partitions. So only the outer few walls are strategically chosen to take the bending and shear, especially the shear. So we'll come back to more on the design of the core wall when we start looking at the lateral system. But you should just recognize that the design of the core, both for architecture, services, and structure, is very critical. And a lot of time engineers spend on this part. Okay. And one of the main reasons cores are there is because of the elevators. Vertical transportation is the key, because people want to get to the tall buildings as fast as they can. Nobody wants to wait for 7 minutes or 8 minutes for an elevator. So they keep adding elevators to make it fast. When they add the elevators, the core size becomes very large. When the core size becomes large, they lose the rental space. So there's a compromise between how many elevators to put, how fast they can go, and how many people they can accommodate. So elevators have become one of the bottlenecks in tall building design. And they try to solve this bottleneck by so many ways. In fact, I will try to invite some elevator company to give you some presentation about elevators, because elevator and core are tightly together, are tied together. So understanding elevators is important to understand the core. Now, in the past, the elevator, still in many buildings, the elevators use cables, steel cables to do that. But steel cable, if you remember course number 1, we have the specific length or specific height. So the cable, for a certain after certain length, the cable will become so large that it is impossible to roll it on a drum, because cable has to roll when the elevator comes in down. It becomes so big, it's not possible. So practically, the cable becomes so thick and so long that you cannot maintain it. And that is the limit on the tall building using the traditional cable, steel cable elevators. Then there was a breakthrough. We have carbon fiber. So when carbon fiber came, the steel cables were replaced by carbon fiber flat cables, very thin, very strong. Now you can go much higher because you can have much longer elevators. But the problem was that the elevators start to shake because the E is less, because it's very long, so extension happens. So the elevators were not stable. So they added a lot of systems to stabilize it. So they also, cables, the carbon fiber cables also reaching their limit on the high buildings. And then there comes the speed. People want high-speed elevators. In a building, like for example, 120-story building, people will expect that it takes no longer than 1.5 minutes. And that means that really, really fast elevators are needed. And in the beginning, before the current, people have to change the elevator 2 to 3 times. So 30 floors, then change elevator, next 30 floors, then change elevator, then next one. Of course, people don't want it, because high floor people pay a lot of money, so they don't want to change elevators. So they start to find many solutions. So then one of the thing was double-decker elevators. Rather than one cabin, 2 elevators, 2 floors, elevators move together at the same time, so they can carry double the load. So some buildings are using those double floor elevators, that they serve 2 floors at the same time. Okay. And so elevators have gone through a lot of changes, and this is the important thing. Previously, the old design of the elevator will require 15 shafts. So the core will be very large, and it's very good for structural engineers because you can use the entire core. The new technology only requires 9 shafts, right? So you can imagine that from 15 to 9, because the elevator technology improved, number of shafts has decreased with better performance. So which means that structural engineers now get a smaller core to deal with for the same height. So which means that structural engineers now have a problem. They cannot rely on the core anymore. That's why they have to find other systems like mega columns, like tube. We will discuss all of them. So one of the reasons structural engineers have to find new solution is because of the shrinking core. As the elevator technology becomes better, number of cores reduces, and then we have to find some other ways to support the lateral loads. And now they're looking at, so this is just the way a typical elevator will work. So you should know that if for a typical elevator, there are 3 things that we need to know. One is this pit, which is needed below the last floor. And this causes problem with the foundation raft, because normally there's a floor raft here, foundation, but this pit has to go into the base, into the foundation raft, and then you need a separate arrangement to capture this one. So this creates a design complication in the design of the foundation raft and the piling system. Then there is a machine room at the top. So you also need another extra space on top of the elevator where the machine room and cables and things will lie there. So this is this thing that these structural engineers need to provide. And there's the counterweight and many things and brakes and so many things. So the technology for elevator is one of the things that as structural engineer, we need to understand. And now they are working on this one. magnetic levitated elevators. They don't need a cable. They don't need anything hanging. They just have a magnetic attachment to the wall. So just like the trains in China and other places, magnetic levitated trains, these are just moving horizontal and vertical. They can move in any direction, right? So they already have a building where they're experimenting. So which means that the elevators no longer need a core to go all the way. And they also are not limited by the length of the cable. They also don't need a machine room. They also don't need a space at the bottom, right? So they just attach to the building and then just keep moving on the rails using magnetic levitation. And this is what now is the future. So if that happens, then we will completely lose that continuity of the core. They will just move, go this way, go this way, go that way, everywhere. So that's what is now in store. Okay, this is the real building where this is being tried now. So this is multi-elevator Tyson group. They present, so you can see here that elevators can go everywhere. And this would be quite interesting that elevator just moves around the building, breaking the continuity that we traditionally rely on. And this was introduced in 2017, already 8 years ago. So now, it's developing further. No cables, no core, nothing is needed for these elevators. And they also, they interchange, so many things. So this is the working of that building that they made as a test case. And then you can also transfer from one elevator to the other and so on and so forth. So highly complicated mechanical systems, like cars moving around the building. Okay, so now because as you can see here that in a tall building, so many people need to work together, we need to understand this multidisciplinary team and collaboration as our basis. And I will tell you a few stories about that. So this is an important point to note. The structure theory is universal. That means whether the building is in US, Thailand, any country, bending moment is bending moment, shear force is shear force, same rules apply, same math, same everything, same analysis can be done, whether it's a steel building, anywhere, it doesn't matter. Finite element model doesn't care about the material, location, or anything. It's just solve the basics. So our basis of structural engineering is universal in time and place. But architecture keeps changing based on the time and also based on the location. So every place architecture will be different, and architecture keeps evolving. As you know, now is the fashion for this kind. Then after some time, the buildings will change. And every country is trying to make different kinds of iconic building. But the job of the structure is to make architecture possible. That means even though our theory is universal, the application is very hard because we need to adapt our systems to changing architecture, changing in the elevator system and so on. So that's the challenge that the structural engineers, even though we know the basics, applying them to all these changes in different locations, different countries, different architects, and different style makes the structural engineering exciting and also a challenge. And that's what we will learn rest of the course. How do we find solutions for all these different variations of architecture and from other disciplines? So if you look at the building systems, we have an architectural system, a basic functional system. We have a structural system, which is the one that we are dealing with. We have a heat and ventilation and air conditioning system, which is a complete major part of the tall building, especially office building, hotels and all. They take a lot of space and a lot of emphasis is given for climate control. Then plumbing and drainage system, water supply, sewerage, all those things have to go in and go out. Fire systems, electrical, electronics, communication system, cladding system. At this point, major part of the building cost and emphasis is given on cladding. How is going to be the outside of the building, glass or whatever it is, how will it connect to the tall building? And the problem is that tall buildings move a lot. as you already know, they deform a lot. Okay, let me see. Let's say it's a 100-story building. How much do you think it will deform in a typical earthquake? 300 floor, 300-meter building. How much do you think it will move at the top? In a strong earthquake, building can move up to 6 meters. 6 meters. So if I'm here, 6 meters is the whole room. So a tall building is expected to, within safe limits, without falling down, without breaking, it should have the ability to move around 5 to 6 meters. Can you imagine that? 2% up to 3% is possible. So it can go as high as 9 meters, right? In extreme case. Still, building should not break, should not fall, should not cause a damage. That's the kind of movement we are looking at. Even for normal wind, it will be more than a meter. Just daily movement of a building of that kind is more than a meter. So if the building is moving that much, the cladding has to be designed to adjust to that movement without breaking, without having cracks, without falling down, without having water. And look at the wind that will blow on it at that height. Look at the hurricanes, the water, the rain, the snow, right? So cladding is extremely important and needs to be designed as a major part of the tall building because it must accommodate the huge movement, it must accommodate huge weather changes, and must protect the people. So cladding system design, attaching the cladding system to the tall building, fixing, jointing is one of the most, I would say, challenging job in engineering. There are a whole branch of cladding engineers who just design the cladding systems, right? Anyway, so cladding system, security system, and then many other specialized systems will come into being. So now you can imagine that in a tall building, so many systems are existing at the same time. And they all have to work together. And as I mentioned to you, each one is, for them, that is their job. They don't care about others. Plumbing people just want to make sure that plumbing is perfect because people will use it. The problem is here now. Structure is the only system which nobody ever cares about because it doesn't affect their daily life. It's going to be hidden and out of the place. Every other system you see here, people will observe daily and they will see and appreciate or complain daily. Elevator is not working today, water is not working today, air conditioning is not working properly, the cladding had a leak, the planning is not good, I could not go to my room, the staircase is not placed correctly. Every system people interact daily, so they know their importance. Structure is the only one they don't even know exists until there's a crack, right? Then everybody runs back. So that's our problem. We design the most important part of the system, which nobody knows or cares about until it doesn't work, right? So that's why we need our structural system, because everyone will need us ultimately to make their job, okay? We have to make the structure so every system can connect on top of that. So there's going to be a big fight between all of these people when it comes to the design and planning and coordination meetings. So this is the team. So this is the client. Normally, they will hire one project consultant because it's so complex that client cannot understand directly what's happening. They cannot deal with everyone. So they need a specialist to sit between them and the team. So another consultant comes in, which is the project consultant. These consultants, so the client will first hire a project consultant. They will then hire all the other consultants and do the coordination, because the client cannot have all the technical knowledge to do that. So the project consultants will come in, then we will have a design phase, we have a construction phase, we have a post-construction phase, and then we have some other services to be done at the same time. So this is the design phase, they will involve so many people: architects, structural engineers, MEP engineers, interior designers, communication engineers, fire safety people, landscape architect, geotechnical engineers, and all the way, right? So there is a whole big team that will work on it. Then construction phase, different teams will come in. We have the main construction manager, another team will come in, contractor, architects, structural engineers, subcontractors, many contractors will come in, suppliers will come here. Then post-construction facility engineers. Facility managers now currently have become the most important people because they look at the building for the entire life. We only look at the building during design phase or construction phase. After that, we are out. But the facility managers or facility engineers have to be on site to make the whole system keep running. So we need facility engineers, and then architects and security consultants will still be involved. And then we finally have some other people. So you can see that about 15 to 20 consultants will be involved at any given time during the building. Now, last time I remember we were working on a building, and then so there's a coordination meeting happens every week. So the client is sitting here, long table, 20 people are sitting here. Normally, client will sit here. This side will be the architect, and this side will be the interior decorator, and then structural engineer will be sitting over there on the corner. Because these people are actually managing, the client only cares about how the building looks like and how the interior will look like. Everybody else is not important for the client because they're going to sell the building based on the work of these two people. Third person is now becoming very important: landscape engineer, landscape architect, because now every building has landscape also as part of that. There are plants on all the floors. So that is the hierarchy. And structural engineer is probably the least important there in the whole team, although their job is very important, but their work is not seen as important. So in one of the meetings, I remember the client, the interior decorator, he talked to the client something. I could not hear. I was sitting very far. And then the client said, "Oh, structural engineer." I said, "Yeah, here." And he said, "Okay, can you, for this building, that column on the corner, it's going up to 9th floor. And can you move it 1 meter and then take it up 5 floors and bring it back again?" And we're talking about tall building, and this is like in the middle of the building. And I'm just curious, what happened? I said, "Yes, it can be done. Of course, you have to say that it can be done." But I said, but may I know the reason? He said, "Yeah, the interior decorator wants the curtain to go around. He doesn't want the curtain to be obstructed by the column. So please move the column away so he can move the curtain around the corner of the building." That's it. I tried to explain that it is a bit, complicated, this one. He said, "Yeah, it's okay, but because he wants it, please get it done." Then same project, the project is delayed, everything is done. Now one floor drawing is held up because the landscape architect cannot decide where they will put a 10-ton tree because they want to put a big tree on that floor. And landscape architect cannot decide where the tree will be. So if they don't decide where the tree will be, the floor cannot be designed for that load. Floor cannot be designed, the building cannot begin. It took 2 weeks for the landscape architect to decide where the tree will look good. And the whole building is held up, right? So that's how the dynamics works in a tall building project. So engineers, you have to be ready to deal with this kind of things. But bottom line is they still need structural engineer to do all of this stuff that they will use later. Okay? But you need to understand everyone and be ready to work with them. So now you need architects. Remember, architect is a team leader for a tall building. So we have to work with them or under them. Then structural engineer, geotechnical. Geotechnical engineer are even below us. Right? Nobody really cares about them, even much less than structural engineers, unfortunately. But of course, their job is very important because ground, that's where the foundation will start. Electrical, mechanical, plumbing, construction, all these engineers are needed for the building, like I said, in that team. Now, this is a work flow. You might think it's the same like that diagram, but this is the team and this is the work, not the same as the team. what kind of work goes into making a tall building. So design work, architectural design, structural design, MEP design, firefighting system, geotech, interior design, and so on. So for each of the design, you need a team, but the product and the team must be separated, okay? Because we will look at the work breakdown structure after that. Then project manager, preparation of, then this is the steps of we are talking about now, second thing, which is called work breakdown structure. So work breakdown structure is that we have to break down the work into as many small pieces as steps as you can, so then you can do them one at a time and then put them together. So the first thing is to identify the team. Second thing is to identify the work. So project, for example, site preparation, approval of the plans, contract administration, project monitoring, quality assurance, quality control, and so on. Similarly, construction, planning work, site work, foundation work, structural work, architectural work, roof work, MEP, fire, and so on. So each step of the work must be clearly defined, and the teams need to be defined. And then comes the most difficult part, which is this matrix, which is called the responsibility matrix. And this is, everything depends on this matrix. Who will do what at what time, and who is responsible, who will check it, who will prepare it, what is the role of each person in each task. So this relationship called responsibility matrix says that, okay, design time, these people are involved, this is their role. Project manager is going to do this one, construction time this was, project management this one, construction this one, post-construction this one. These people are responsible for approval, these people are responsible for preparing, these people are responsible for helping, and so on. So you put everything on paper like this one. In fact, any complex job requires the division of work and the division of role and division of people, all represented in one matrix, right? Responsibility matrix. And then once this is prepared, then you know exactly what you will be doing in any of these tasks when they are being done, and what is your exact role. So this is a totally responsible, this is partially responsible, and so on. This is just a sample. So now, not when you design buildings like this one, you cannot just only think about your work, because your work is tightly connected to everything else. So you need to understand what other people are doing, what they need from you, what is their role in their work, and what is their role in your work. So the whole system has to be understood before we do a project of this kind. So now let's look at the efficiency and sustainability, because ultimately the design has to be efficient and has to be sustainable, right? Before that, earlier, only efficiency was enough. Now sustainability also needs to be considered. So this is the last part of this lecture. Then we will start the structural engineering part. Right now, we are still in the introduction. Okay, so when we target efficiency of a structural system, we actually target efficiency at every level: materials, cross-sections, members, and structure. And this is, you can say, kind of a micro level. This is the global level, because the structural system you choose, type of member you choose, the arrangement of member you choose, the cross-section you choose, composite versus reinforced, and so on, and the material finally you choose. Everything together will determine how efficient your structure is and how sustainable your structure is, right? So we need to understand that those two aspects from the top to the bottom, and every decision that you make here or there is going to affect both efficiency and sustainability. Any decision. We just don't know that. We may not know that, but any decision, design decision that you make as a structural engineer will affect both of them. Efficiency includes safety. Sustainability includes environmental stuff, of course, right? So when I talk about efficiency, I mean disaster resilience. I also mean safety. Everything together, performance, and sustainability is the long-term effect of your decision. Like, for example, if you're choosing a cross-section and you say, okay, I'm going to, the decision between using high amount of reinforcement and small section and low amount of reinforcement and large section is going to affect the carbon footprint, is going to affect the space utilization, going to affect the construction, going to affect the amount of material, cost, and everything. So it's a small decision, but it will affect everything. And we should have a way to measure those effects. So efficiency of tall building can be assessed at strength and stability, stiffness, ductility, redundancy, durability, constructability, flexibility, sustainability, cost effectiveness, as well as the aesthetics. So there are many ways that you can measure the efficiency or the value of your design. So we talked about the components. So if this is a tall building, then we have these components that we have to deal with. We have to deal with the beams, the columns, walls, and slabs, at least minimum. So we talked about the slab options, reinforced concrete, post-tension, steel deck. We will talk more about them when we talk about the gravity load system starting next lecture. So we have to choose one of them. And within that, you have to choose many systems, right? Beam slab, flat plate, and so on, baffle slab. So there are many sub choices that we need to make. Each choice will give us different efficiency. Beam, same way. So we have reinforced concrete beam, post-tension beams, composite beams, and steel beams. Choosing between them, first of all, we have to choose a system. Are we going to use beams or no beams? If you choose the beams, then what kind of beam? What kind of section, what kind of material we will use? So all of them have very different impact on construction, cost, sustainability, and everything. And most currently, people are favoring steel beams or composite, sometimes composite and post-tension. Then column. This is where one of the major decisions will lie which column type to use. And as I mentioned to you now, composite is where people will be going more because it is space efficient and also it's cost efficient. Not cost efficient actually, but overall cost is less if you look at the whole cost of the structure, not only of the column. Cheapest is still reinforced concrete. If you just compare cost by cost per cubic meter of the concrete, this is still going to be the cheapest. Steel is very expensive still. Then shear wall. Shear wall is, and like I said, elevators are normally shear walls, but not only that, we also add other shear walls, and their design also will control the speed of the construction. Normally, the core wall or the shear walls are made before the building, and the building is then followed and connected because they are formed very fast, quickly, and then the building follows later. So making the shear wall as fast as possible and as economical, as thin as possible is very important. And that's why this new system of the composite plate, steel plate with no reinforcement has come up now. Very recent. People just thought, okay, why don't we just put steel plate on both sides and no reinforcement? This is the traditional one. This is the mixed or the composite core with the steel section inside, but still concrete outside. So these are the main three options that we will consider. And currently, this is expensive, but very fast in terms of construction, and the size is small. So how do you measure efficiency? There are many measures, and we will just talk about some of them. First one is stiffness and softness, because like I said, building movement is one measure that we have to start with. That we cannot allow the building to be too soft and too stiff. So that softness has to be in or stiffness or softness, either way, has to be in a very sweet spot. Too soft, not good. Too stiff, again, not good. And one of the measure for that is natural period of the building. So one of the things that we will be always looking at as an efficiency measure, the first efficiency measure of a structural system is going to be natural period. What is the natural period of a building? You know what's a period? What's a natural period? What is the definition of a natural period? So time to complete one. So building is moving this way. It's if you start from here and then it goes this way, and come back to the same position, the time taken to complete one cycle is natural period. Okay, what is the natural period of a, let's say, 300-meter tall building? Acceptable natural period of a tall building. For 300 meters, it could be as long as 8 seconds. So once again, just like your estimate of the displacement, the estimate of the natural period is not so good at this point. So imagine 7 or 8 seconds it will take for the building to complete one movement. You know how long as it is? 1, 2, 3, 4, 5, 6, 7, 8. That long it will take for the building to move one time really slowly. For a building which is just 4 or 5 story, how long will it take? Just like that. Or a small building, maybe 0.1 second. So you can see that the tall buildings move really slowly, but we cannot let them move too slowly or too fast. So we have to bring the natural period in a very good range. And once we control that, most of the other things will start to be controlled. So natural period is one measure, efficiency measure, starting measure, and second one will be the drift, which is related to that. Okay. So both drift and natural period is the first two measures of structural efficiency that we should look for. Structural. And then how tall the building can be based on a material. We talked about this one a little bit on the specific height kind of a thing, that once after some time, that material will become so big that no space will be left to rent. So this is roughly for concrete, 1500 meters, concrete with very high strength, 3000 meter and so on. So material is still not the real problem yet. High strength materials are still okay. It is the other things that will control. So we are not limited by material strength for the height of the building. We can go up as high as 5 kilometers even now, right, with the current material technology. So which means the material strength is not the controlling factor for height of the building. It is going to be other things that will limit it. Elevator is one, and natural period is second, drift is another one, and so on. Okay. So this is it's a nice diagram showing that what is the ratio of different, and this is one more important efficiency parameter, which is called the ratio of the floor area and the structural system, HVAC system, core system. How much is the services and structure taking away from the rentable area? Because client can only sell the rentable area. They cannot sell the serviceable area. So that means the efficiency of the design is measured by these white dots rather than these gray dots. Gray dots is the area taken by system, structurals or another system, and white dot is the area left for the rent. Okay. And you can see here that lease area is roughly 70 to 80% should be targeted. That if the floor area 70-80%, between 70 to 80% should be available to be rented. That means you are left with about 20 to 25% of the area, which is still large, that you can use between that. So elevator area, stair area, shaft area, structural area, about 5%. This is very rough numbers. Just give you an idea that how much of the area that you can use. So for the column size, you can only use that much area. So material has to be based on that. You cannot make the columns larger or structure wall larger than that. Okay. So this is the next efficiency factor. After that, how much of the floor area did you eat up in your structure? So if some design uses 7%, some design using 4%, 4% is better than 7%. So people will immediately check your structural design based on how much floor area did you consume. There are other matters. I'm just going step by step. So this is the next important measure on how much percentage of the floor area people can take away. So they will target elevators, they will target structures. Core program area is 12%. This is other things, total stuff, MEP and all of that stuff. So so we have the natural period, we have the drift, and we have the structural area utilization as few measures of efficiency. So when you do your project, you should report all these things as part of your comparison. When you compare systems, you should compare these numbers. So now the question is, how do you select structural system amongst many systems? And we have to think of everything, because every decision that you make will affect everything else. So building services, building system, all the professionals involved, we have to study that. I showed you already. Functional structure is part of that. Other systems also depend. Then when we have to look for the structure, we have to look at the basic requirements, planning requirement, structural requirement, construction requirement, and designer's attitude. So which means that all of this will affect the structural design. And in workflow, you have to look at the integrated design and conflict resolution and many things. So it's a complex diagram, but it's not something that you can make in isolation that, okay, I choose to do this because it will affect everyone else. So you make this decision considering the whole thing. Now, I put here designer's attitude as one of the criteria. Designer's attitude means some designers are more daring, some are more conventional. So that attitude will change, will affect the final design. That's the difference between a good designer and not good designer, is their attitude towards all the efficiency criteria. How do they balance this one? And then, like I said, there are further ways to do that. This is the overall approach. And then there are many methods to make their decision on that. Expert systems. When I started studying a long time ago, expert systems were very popular. So expert systems were that you interview expert. This is before AI and everything. So you interview many experts and to see how they make the decision, and then you convert that into a program, and then you try to emulate experts, and those were called expert systems, right? So now they're out of fashion because AI has taken up. Rich pictures is another concept that when you make a decision, you don't make a decision based on what you see here, but you go very high. It's called bird's eye view. You go very high and look at the whole picture before you make a decision where one thing fits, right? And this is one of the problems with engineers. People say that we have a tunnel vision. We only think about what we are doing. We don't see the impact. Architects have a very broad vision. That's the main difference, because they are looking at the whole project, every part. We are only looking at one system, right? So to make a decision, we must elevate ourselves and look from the top and create a rich picture which includes every possible thing that is going to affect your decision. Mathematically, AHP is very useful. Analytical hierarchy process is a kind of a mathematical way to make decision. And the example is, I normally give this example: telephone, cell phone, buying a cell phone. Okay, if you want to buy a cell phone, how will you choose a cell phone? There are so many options there. Brand, memory, brand, processor. See, right now you have two different views. So you can see here that your criteria and his criteria for choosing a cell phone are very different, right? So now you three can never agree on which is the best phone, because your evaluation criteria is not going to match. So the system has no intrinsic property, good or bad. And that is the point that you must understand, that structural systems have no inherent good and bad things. It is how we value them, what is important to us, make a system better or not better. So for you, when you buy, somebody will look at the cost, somebody will look at the color, somebody's screen size. So everybody will have a different way of choosing a phone, even though there should be one universal single best phone. There isn't, right? Same thing for the structural system. There is no universally best structural system, because every project is looking at it from a different angle, which is called weightage, what is important to them. So same system may be good here, same system not good there. So that is the AHP is a way to look at the systems, giving them weightage and evaluate them, and finally come up with the best number for the criteria that you decide. Okay. So we use that often in system selection, AHP. Then fuzzy logic, you don't say bad or good, you say, yeah, maybe gray area. You can consider gray area into your evaluation, not black and white. So it's fuzzy logic. Of course, AI now is one of the best tools based on experience. That based on data analytics, purely based on data, data-driven decision making. Value engineering, it's an old field, but still there. You evaluate the value of everything on many criteria. It's similar to AHP. And the design efficiency could be just very simple. Which structure is most efficient? We will take that, not worrying about the cost. So this is actually, as you can see here, to choosing the best system is no simple task. First of all, there are many systems to choose from, and then many ways to select the system, and everybody can come up with a different answer. And that's exactly the point. That's why you have so many buildings, each with different system. Nobody's using the same system everywhere, right? Every building has a different system because of these reasons. They all come up with a decision, all think they are good, all think they're right, otherwise they will not make the decision. So you can reach different decisions based on how you start and which method you use. So please remember, there is no single best structural system. It depends on how you evaluate and what is important for you and for that project. Okay, this is one of my students. She did a thesis. She's an architect and did structural engineering here from Nepal. And her thesis was, because she has an architecture background, I asked her to develop a system selection, do a thesis on how best to choose a system, both architecturally and structurally, with the two backgrounds. So this is the rich picture concept, where if you want to choose, for example, the floor system, how many things you should consider, right? So she starts with architecture, and she starts with structure. Then within structure, you have planning, basic requirements, structural requirements, foundations, lateral system, construction requirement, designer's point of view, building plan, and so on. So she tried to create a relationship between how complex is to just choose whether you want a flat slab or a beam slab, because it will affect everything. And this is very important here, designer's attitude and experience. So I remember when I started my first job, maybe I told you this story already. So in that company, they were doing many buildings, and every building is beam slab, beam slab, beam slab, and column, same system. And then we had a hospital. And then I said, why don't we think about using flat slab or flat plate here? And because it's a long time before computers and everything, I'm talking about 1982. So I went to the chief, I only joined the company maybe 3 months ago, 3 months before that. So I went to the chief structural designer. He has 25-year experience. And I thought, oh my God, so much experience. And I said, okay, I want to use flat slab here. He said, no, you cannot. I said, why not? He said, because we don't know how to design flat slab. We only know how to design beam slab because we don't have any computers, anything. Flat slab is very complicated to design, so we don't design it. So just because the engineers did not have experience to design flat slab, they never designed any building for flat slab, even though that was a better system for that project, because for hospital, they needed a lot of flexibility in the air conditioning and the other system below the slab, and beams were obstructing all that ducting. So, but they didn't want to do that because engineers don't have the experience. So sometimes the best solution is not adopted because engineers don't have the knowledge, or they don't have the experience, or don't have the tools to design it. It's just as simple as that. So that's why this is also important to make this decision. Then AHP, as I mentioned to you, this is very, very useful approach. That means you take different alternatives, you do the ranking, you based on economy, ecology, technology, risk. So you take many factors, you attach them together, and then this whole process, it's just, I'll give you a diagram, but actually it's a very simple thing. You can do it on an Excel sheet, ultimately. It's just a comparison and rating through 3 levels of multipliers, and that's, it can be done. So when we come to that, maybe I will show you the equation to do this one. But AHP is one semi-mathematical way to do this within certain agreed framework. And then, of course, artificial neural networks now. And we did this 10, 15 years ago already, that we took a lot of architectural layouts, we did that response and then linked them together through ANN. And then you can just bypass the whole thing and find the best solution based on the previous performance of your previous data. So that is, of course, now it's not a big deal, but 10, 15 years ago, it was a big deal to do this. Okay, so some structural efficiency indicator. Coming back to now, how do we measure in real numbers? What is it that we are looking for? One of the things is the structural volume over building volume. This is one measure. How much? Because if you just compare the area of the column is not enough measure, because you're forgetting about the slab thickness and beam that used the space. So normally a better measure is structural volume versus total volume. How much of the building's volume did the structure consume? So if you consume a lot of volume, that means you ate away the space which is available for living. So one indicator is structural volume divided by total volume. Second indicator is structural area, combined area of shear walls and column divided by the floor area. That is another measure. Then reinforcement ratio, how much reinforcement is there per cubic meter of concrete? And then how much cubic meter of concrete, because this will tell you cubic meter of concrete per volume. That will tell you reinforcement per cubic meter of concrete. So combine these two can give you a very good indicator of what the cost and what the efficiency is. And then we have the DC ratio, demand and capacity ratios together with that. So you have measures on volume, you have measures on area, and you have measures on quantity, steel reinforcement within concrete, and then you have measure on the performance. So combined together, these four indicators, if you can evaluate them well, you can compare buildings' efficiency. Because some building may be very cheap, but DC ratio is not good, is unsafe, you cannot accept it. So everything has to be in a good range. So you have to have a safe building, DC ratio acceptable, and reinforcement ratio not too high, area not too high, volume not too high. So that's how you can measure the efficiency over these four categories. These are real numbers. And good designers, good designer companies always keep these numbers on their fingertips. And some engineers, some designers, not a good practice, will go to a client and they ask, oh, what is the reinforcement ratio are you getting? The client may say, okay, I'm getting 120 kg per cubic meter. Oh, I can make it 110 kg per cubic meter. Give me the project. And I will take 5% or 10% of the saving. So some clients are inclined to that and they say, okay, go ahead. If you can reduce the cost, you can take 5 to 10% of that. So that's not many, but some engineers do that. It's not actually a good thing, but some engineers do that kind of thing to get the project. They get the project based on reduction of one of these critical points that the client is concerned about. But we have to make sure that the performance is not reduced. This is some numbers for you, just roughly. So this is the average numbers from some data that we have. So this is the average number of floors for that data. Let's say this is the project done by AIT, the last, before 5, 6 years. Based on that data, average building floors were 58. Average height was 196 from those projects. And height over L max is 3, which is very low, not very tall. Minimum this one. Then slab thickness, average this one. Tower area over podium area, this one. Podium. The point I'm trying to make is that if you keep this data for every project in your database, then you can have very good indicator of the experience. You can use this data to train the models, and you can also learn what is the average range. Is the building high range, low range, and so on. So it's good to save this kind of information from the projects that we do, right? And and we should train ourselves to have these numbers. So when you look at the design, you can say, oh, this is a good design. This is not a good design, because you have some idea about the range of the numbers. Similarly, beam length per area, equivalent beam thickness, beam volume, concrete volume, wall volume, column thickness equivalent, column area ratio. So you can calculate many of these indicators from a building design and keep them in a database. They become your efficiency indicators. And then you can compare them across the projects in global detail or very much local detail. So we must always remember that ultimately our design must be viewed with some level of efficiency, whatever that is. We cannot just design something in vacuum and don't care about efficiency. So however we measure the efficiency, we should know what measures are and where do we stand. And because somebody will check this number. This is the wall thickness, wall minimum maximum thickness, and so on. So you can see here that this is all extracted from existing projects. You can extract this data, you can store it, you can analyze it, and then you can see where each building is, right? So much can be done based on this data. Okay, the last item on this one is this one. As I mentioned to you, efficiency alone is useless without the structural performance. And one of the indicators of structural performance is the utilization ratio or the demand capacity ratio. Demand capacity ratio means how much is the moment, what is the capacity, and how many places we utilize this capacity. Let's say there are 100 beams. Okay, let's look at the second. So first of all, let's see. If the demand capacity ratio is more than 2, is unacceptable. If it is less than 1, it is good. If it is less than 0.5, it is uneconomical. So we can see that, okay, demand capacity ratio is an indicator of safety and efficiency at the same time. And that's why this is very important. So we have to make sure that our DC ratio doesn't cross the limits for safety and also doesn't go down for economy. So this range is economical and safe. This is uneconomical to safe. This is unsafe, economical. So this band of distribution is very important. And then we can then go one more step and create this table. We can say in my building, I had 178 columns, 16%, of the total columns, 178 are less than 0.5. That means 16% column were uneconomical, right? Because their DC ratio was less than 0.5. 49% were in a good range, this one, and 31% in a very good range. They utilized the capacity well, and they were not uneconomical, they were also safe. And then 1% were over 1.5, kind of unsafe on the edge, right? So this kind of distribution, calculating this distribution, will give you a very good final indicator of safety, performance, and utilization and cost and everything. So ultimately, we should target that we have most of the structure elements lying in this zone for best combination of performance and cost. But sometimes it's not practical to do this one. Why? Because if I want to bring all these columns in this range, I may have to reduce the size of some columns. But it's not good because construction-wise, it will be very difficult to make every column different size because you have to make formwork, you have to test. So on a global size, it's not possible. So that's why the other decisions will come in. You cannot alone use this one. That's why it's important to make this decision considering everything together. Architect may not want you to change every column. The contractor will not like that every column is different size, right? For construction, for verification, and so on. So the design is far more than just looking at one element at a time. So this is not cost effective. This is not safe. This is ideal. Last item, last slide. We have many factors: axial capacity ratio, building aspect ratio, carbon emission per unit area, perimeter enclosure factor, structural plan density index, bending rigidity index, right? Ultimately, we can evaluate the efficiency at very high level ratios, including especially carbon emission per unit area. Now it's easy to calculate because you have calculated the quantity of concrete and material steel. You know their carbon emission numbers. You can now also calculate that. So it's quite possible that steel, using more steel may be uneconomical, but less carbon, right? So if somebody is saying, I want a more sustainable building, I don't mind paying more now, fine. You shift from a conventional economy to sustainability economy, right? So that's why this measure is also now important, right? So this is the big picture of the final efficiency stuff. So we talk about 8 dimensional parameters: serviceability, safety, economy, environmental, social, adaptability, frame, resilience, many things. So you can go on and on and on, but going higher and higher level. Okay, that's it.